Welcome back to the Hyperbolic Coding Coalition. This is day 71 of Coding Coalition. This is day 71 of Daily LeetCode. Right. Today's video is going to be called No Days Off 5 Homecoming. Right. So there's been a trend in these video titles, and largely we are borrowing, or we are being inspired by the Tom Holland Spider-Man series. And today is going to be No Days Off, the final movie in the saga, and it's going to be called Homecoming, right? Because we are now back home. The setup has returned. We are receiving a buff from our natural location of origin. So we have a buff. Previously we were experiencing a debuff. The West Coast gives us a debuff, right? But since we're from the East Coast, we're now receiving a buff, and this buff allows us to solve LeetCode problems at a pace which is 6% faster than usual, right? I also have some reflections. We did coin change the other day, and we did BFS for it, and the implementation was pretty slow. And yeah, I posted in the Discord. And we have, the legendary assortment of individuals who are able to answer any algorithmic computational question. And I couldn't figure out why this approach was pretty slow. But I think it is because of what they're mentioning, right? Legendary algorist himself, the copy ninja, mentions that we are indeed using a queue, right, instead of a deck, right? And with shift, right, the worst case is linear time, right? So it's kind of like n squared time low key, since we're going to be visiting, right, let's just say n nodes, and shift is actually going to slow us down quite a bit since we're shifting down elements. So I'd like to try a version of this where we re-implement it with a deck. So hopefully the next time we do coin change, we can immediately implement a deck on the spot, maybe with something like 2 pointers. And I think we could do that. I think we could do that now. But it's important, I think, to make sure that we're always working on the highest priority thing. And would it be important to implement a deck to see if we could do this? Yes, that might be what we do today. So we might implement a deck just to make sure that we are understanding that is exactly why I was going slow. Maybe not a deck. I'm thinking to start, we're going to implement something like a linked list or a linked node, right, that gives us constant time insertion and removal at the front, and it also at the end. So I think that's what we're going to do today. And then additionally, afterwards, we're going to be back to our usual schedule tomorrow of doing 1 hour, right? Reading our system design, right? Reading our ADM. On vacation, I did go down, right? I did dial back the grind to just doing LeetCode problems and just reading some engineering blogs from some top tech companies when I had a chance. Something about system design is very interesting. So yeah. And then tomorrow I think we'll be back into rhythm, severely jet lagged. I mean, it is 9 p.m. It feels like it is 3 a.m. right now. So yeah, the brain calibration process is all over the place. But luckily we have our buddy Thomas to save us once again. He mentions that, I mentioned yesterday that there was a problem we did called flattened 2D vector, or flattened 2D matrix, I think, which had a lot of dislikes, which someone in Discord mentioned we should have skipped. I think was actually Copy Ninja, right? When a problem has a lot of dislikes compared to likes, right? Maybe we should skip the problem. Maybe it's formulated incorrectly. Maybe it's tough to follow, right? All things to consider. But Thomas mentions more dislike is better because people hate it. Why is that? Because it made them uncomfortable. And he has a point here. He does indeed have a point, right? I think there's always a level with LeetCode and just doing something to get better at it, right? Where, maybe you're put in an uncomfortable position, or maybe something isn't formulated a way that you're familiar with. So you end up making some mistakes that, you feel like you shouldn't have, right? But sometimes just getting uncomfortable is a good thing. So while some problems may have some legendary dislike rates, it's probably important to still do them anyway. But I do think the fine balance is placing those problems towards the end. Because coin change, right? This is a legendary problem which must be done, right? And it's really just a shortest paths problem. So that is going to be useful in many, many, many ways. Unlike other problems like evaluate division, which actually have never been solved. or no one has been able to prove that they have solved it live. So evaluate division will be the final boss on this channel. So maybe after we've completed all LeetCode problems, we'll be able to solve evaluate division. I also think it would be pretty cool if we did more string problems. I noticed that while I have some intuition on some methods to go about solving string problems, I definitely haven't done enough of them, right? And I tend to get caught up in some edge cases that I should definitely just have a better mindset about attacking. So yeah, I would say today, right, we have one card due, which is binary tree vertical order traversal, which we can definitely do. But first I want to see, right, if we can implement a version of a deck or just some data structure that's going to give us constant time insertion and removal at the front as well as at the end, which hopefully should make this implementation of coin change much faster, right? But as always, you're going to want to join the Hyperbolic Coding Chamber / the Hyperbolic Coding Coalition. This is a very, very important coalition that is growing very quickly to hopefully empower all people of all denominations to work on algorithms, to learn, to get in the habit of trying something you might be uncomfortable with, like a LC hard. I was printing my boarding pass to get on the plane, and it was hard not to mention the gentleman who was taking my bag that I've solved at least one LC hard. And I think that is really what we're getting at in the Hyperbolic Coding Coalition, that sometimes it's hard to admit, right, when you're talking to people that you did an LC hard earlier. So sometimes people just don't know the struggle of the LC hard. So yeah, so as an aside, that's just so we have coin change to do today, and then yeah, we have coin change. We're going to try and implement a deck today, and then from there we're going to try and do coin change. We're going to try and implement a deck, and then if we have some extra time, we'll try and do binary tree vertical order traversal. And also, I also think there's a lot of problems that we now are able to solve that I think we should now be including in our problem, that we should start creating tutorials for. I had originally created around 30 to 40 tutorials for problems, and I feel like I definitely have added more to that list now. And I kind of would like to have a video for those problems as well. So maybe we'll have to try and mix in something like that, where we can post a daily video as well as a new explanation video that maybe can help, so, or maybe I can cut up the videos I've already made or problems I've already done, and just those will be the the versions that I teach. But yeah, I don't know. We're still working on a lot of things. Like we said, the stream could be cool. Maybe if everyone was working on problems together at the same time, that could be pretty cool. So yeah, I'm just going to jump into it today. So we have 30 minutes on the clock. Make sure to join the Hyperbolic Coding Coalition. And yeah, let's jump into it. So we were taking a look at this yesterday, right? We have coin change, which pretty much is a problem that is giving us two inputs. We have coins, which is an array of denominations of coins. We have a goal amount, which is 11. The goal for this problem is to find the smallest number of coins we can use to create this goal amount given the denomination of coins. Right? The smallest number of coins you can use is 3, because if we use 1 5 coin, 1 5 coin, and 1 1 coin, we can make 11. So that ends up being really useful. And so another way we visualized it was as a tree, right? Where you have 3 potential trees, or S potential trees, depending on the number of denominations, right? And we basically want to use all these trees and basically find how many which each of these trees, what is the shortest path to this node 11, right? It's going to be an n-ary tree where each node is represented, right, by the parent node plus the denomination taken to get there. So we start at node 1. We have 3 denominations, 1, 2, and 5. And so our first child is also visiting 1 again, which means our total sum is 2, right? Presumably there is a path to 11, right? Simply by adding never ending ones, this path would be of length 11, which definitely is not the shortest path. So we rephrase the problem by phrasing it as a shortest path problem by searching from the source, from the target. So what if we searched from 11 instead, right? Then there could only be a certain number of paths, which would allow us to get to 0, right? It'd be a very small number of paths. But after rephrasing the problem that way, right, we decided to use a breadth first search because a BFS tends to have the property of allowing us to find the shortest path, right? Just because the nature of how we expand nodes. We typically add nodes, right, to a BFS, right, and process them the soonest. So just by the way we process the nodes, we end up finding the shortest path starting from our target node. So since we're starting from 11, whenever we reach 0, we can be certain that it is the shortest path to 0, just because of this property of breadth first searches. After we did that, we implemented a version of it where we were counting downwards 11 to 0, and a version that we were counting upwards, right? Starting at 0, we can see that this is the version we currently have, right? Because the version where you're counting upwards requires you to have this for loop where we push versions of coins onto the root queue, right? So we can delete that, uncomment this, and we'll just change some logic, right? And instead of cur equaling amount, we're going to want cur to equal 0 since we're counting down from amount to 0. And we're not going to say cur plus coin, we're going to say cur minus coin, right, is less than 0, then we want to continue. For example, if we go to node 2, right, and we subtract 5, that's going to give us -3. We're aiming for 0. So if we go below 0, right, we're going to want to skip adding this node onto the queue, right? And so I think with these changes in mind, if we restart, if we click run, we should get a positive answer, but it should be relatively slow. Okay, so there's definitely a bit of lag at play, because now that I'm running it, it's around 500 milliseconds, but we were running it the other day, it was like 1200. It's about 600, so maybe if we use the deck, right, we'll be able to go faster. So let's implement it. I'm thinking the version I'm thinking of using is one that's going to be based off of a linked list, right? Because we want constant time insertion at the front and the end. So one way to do that is just with a linked list, right? So yeah. So what we can do is create a node, right? And this node will be very simple, right? It'll have a value, right, which will be the value stored at that node, right? It should be a number which starts at 0. Then we'll also have our path length for this particular node, right? And this is just important because we're going to be replacing this queue with this linked list, right? And so we want to be able to store the same amount of data, right, which was an amount, right, and the length of the path so far. So our constructor is going to take two values, right? A value, right, which is going to be a number, and a path length to start, which is also going to be a number. We're just going to say this dot value equals value, right? This dot path length equals path length, right? And then we're going to have a doubly linked list here. And I think that if we have a doubly linked list, we can actually replace elements, right, just by having access to the element we want to remove. We actually don't need to be able to do that. Actually, we do, right? Otherwise, when we add an element to the end, we're going to have to, well, let's think about it, right? If we have an element at the end of a linked list, let's say 3, 2, and 1, right? The element at the end of the linked list is 1. Let's just say we have access to the tail node, which is x. If it's a singly linked list, right, we'll have to iterate all the way to 1, right? And then we can add a node here, right, like 0. If we have a doubly linked list, we can have access to tail, immediately check backwards, right, and load that value in. So we definitely want a doubly linked list. So we'll say next, right, which is going to be a type node, going to be equal to null. We'll do the same, which is going to be prev, which is equal to null. Then we'll create a simple class called LL, right, which is just going to be a linked list, right? And we're going to have head, which is going to be equal to node. So we'll say new node, right? And the value it's going to have is going to be, let's just say it's negative infinity, right? And it has a path length of negative infinity. And we're going to do the same for tail, right? The constructor is not going to have any properties, right? And once we create the head and the tail, we're going to want to link them together, right? So head.next is going to be equal to tail, right? And tail.prev is going to be equal to head, just to set it up to start. Then there's two things we can do. We can do shift, right, which is going to return a node, right? And we're going to take an element off the front. We're going to add an element at the end. So we'll just say push and shift, right? It's all we really need to start. And what it's going to take in here is going to be a node, right? So how would you do this, right? Let's say you have shift, right? If we do shift, we also want access to the length, right? So I have another property called len, right? Which is going to be equal to a number, which is going to be starting at 0, right? And we'll say this dot len equals 0. And we're going to want to add this to all of these. And then, right, whenever we remove an element, right, we'll say if len is greater than 0, right? We want to do some work and then return it. Otherwise, we're going to return null, right? We'll do some work and we're going to say len this dot len minus equal 1. Whenever we push a node, we're going to say this dot len plus equal 1, right? So now we have just length set up so we can get that, right? And then we're going to just have a length. Actually, we'll just have access to len. So right, so shift, which is going to get an element from the front, we have access to head and tail, right? So let's just say we have h, right, 3, and then tail. All right, so now we want to take an element off the front, right? So how do we do that? So we can say temp, right, is equal to head dot next, right? So this is the element at the front. Now we have access to say temp, right? Then we want to say head is head dot next is now going to be equal, right? Because temp is going to be 3. Right now we want to set head to the value after 3. So say head dot next is equal to temp. So yeah, temp is equal to head dot next. We have 3, right? Then we're going to say head dot next now going to be equal to t, right? Then we're going to say this dot length minus equal 1. Then we can just return temp. Right, so that seems to make sense. Now let's say we're pushing on to the end, right? What are we going to want to do, right? So we have access to tail. Like we just want to do this dot head. We have access to tail, right? And so to add an element at the end, what we actually want to do, right? We want to say tail dot, we want to save our previous value which is 3, right? So temp is going to be equal to this dot tail dot prev. So now you have access to 3, right? Now we can just say this dot tail dot prev is equal to node, right? Effectively inserting this 2 here, right? But now we need to do, right, is say temp dot next equals node. Now we need to line 3 to 2, right? And we line 2 to 2, right? T's previous to 2, right? Now we just need to make sure. So we have access to 2. We set T's previous to 2, which makes sense. We set 2's next to T, right? And now we need to basically, wait a second. We have this dot tail dot previous equal to temp, so that would be 3, right? Then we say this dot tail dot previous equals node, which is 2. Then we do temp dot next equals node, so 3 goes to 2. Right, now we need to do node dot next equals this dot tail. A little convoluted, but we're just saying that we get 3, right? This dot tail. Well, we want access to 3, and then we actually set this dot tail dot previous, right? Its previous pointer, this dot tail dot previous, this dot tail dot previous is equal to 2. So we say temp, this dot tail dot previous, which is 3, right? Temp dot next equals 2. Then we want to say node dot previous equals temp, right? And then we want node dot next equal to tail, and then this dot tail dot previous is equal to 2, right? So we get 3, right? We say 3 dot next is equal to 2, right? Then we say 2 dot previous is equal to 3. So these two both are now pointing back to each other. Then we say 2 dot next is equal to tail, right? And then this dot tail dot previous is equal to 2. Okay, and then just to make sure this makes sense, we'll create one print function, create a temporary pointer, which is equal to this dot head. We'll say while temp not equal null, right? We're gonna say while temp does not equal null, right? And temp does not equal this dot tail, we're gonna do console.log temp dot value temp equals temp dot next, right? So this should run since we're not actually using anything yet. Forgot this somewhere. We did. Okay, so just to try it, we'll just say const LL equals new. Const LL equals new. We're gonna say LL dot push new node. Right, and we're just gonna have, let's just say 3 nodes. We're gonna say LL dot print. So we get 1, 2, 3. Now let's just say, right, we do ll.shift. Right, we take an element off the front. We should print 1 here. Then we push 3 and then we print it. Oh, we probably want to print ll.shift.value. Okay, so we push 1 and 2. We take a value off the front, we print it, and then we push 3, and then we print the whole thing, right? And then I think if we do one last thing, if we do console, right, console.log ll.length, we should have 2 here. Oh, okay, so we do. So it looks like it's working, right? So we'll see. So we replace we'll replace Q with LL, and we'll make this way smaller so we can actually see what we're coding. We'll say, well, LL.length is not equal 0. We're gonna do LL.push, a new node to start. The new node's value is gonna be amount, and its path length is gonna start at 0. And then instead of Q.shift, we do LL.shift. And we're just going to have node, I'll call it node.value. Then we'll add node.value. Node.value equals 0. Let's say node.value minus coin, that's 0. And then instead of len, we're going to return node.pathlen. So we're doing the group of tuples thing here. So what we could do is just compress this all, right? Instead of doing q.push, we'll do ll.push. It'll be a new node, right? Where the value, right, is going to be node.value minus coin, right? And the path is going to just be node.pathlength plus 1. This.head.next. So when we do shift, this.length is greater than 0, right? Then we're gonna get this.head.next, this.head. I should have used the iPad, could have drew this out. When we push it, we're going to say temp is equal to this. Our problem is saying that this.head.next is equal to temp.next. Not read properties of null reading next. That is very possible. No, it's actually not possible. If we have a node like this, like h3t, we say temp is equal to this.head.next, which is equal to 3. We say this.head next is equal to temp dot next. Temp dot next should be fine because it could be null, right? Maybe that was the problem with this portion right here with null. I actually don't know what problem we're solving here. I'm wondering that if it's because I'm returning null, because this operation should be possible. Let's go ahead that next equal to tail, this dot tail dot free is equal to this is saying that this dot head dot next primary properties of null reading next in shift. See, temp is equal to this dot head dot next, which would be this node here, which would be 3. If that's the case, this dot head dot next, which is 3, right, this dot head dot next, right, which is this pointer right here, should now be pointing to temp dot next. So you know what we'll do? Maybe we'll do this dot print. Then we'll run it again. So last time we do a shift, right, the queue is empty. So maybe there's one thing we want to do. So we want to say if node I'm just guessing. Canary properties of null. So what's the case? Our goal amount here is 100, right? We end up printing node.val with node.path length, right? Then we add a node value, return the path length. So it's quite literally on the first run of no, it's not actually. ll.shift. We print 100. because we print the entirety. So we print, right? Only 100 exists, right? Then we return the node that's there, or the node does exist. Then we print its value and its path length. We haven't seen it before, so we add the value and we push these values on. So maybe something's going wrong here with when we push. If that's the case, we'll do LL. Yeah, I'm just not understanding. We're clearly getting past this point, but for some reason, if we do any work here, then it's too late. What if we just skip? If we don't do any work here. So what if we do ll dot print up here? I think another thing that is strange, we shouldn't even be getting negative infinity and negative infinity, since that is the head and the tail. We never return those values. So how are we even returning that when we do shift? We say temp is equal to this dot head dot next. This dot head dot next. Something is very wrong here. I'm very confused. I think we should have drawn this up. I did not think that this would give us so much trouble. Definitely don't need this part here. We push a new node on. what if we print our list before and after I know they have a debugger. So at this point I'm very confused. So I push the node on, right? I print it. We're just gonna add a break here so we don't waste any time. So 100, 100, 100, 100, then 199, right, then 199. Now what if I do ll.shift, I remove this node and then we print its value. And then we'll do ll print again. Something is wrong with this line now. We have console.log, right? We have the backtick pre-insert. We have the $ curly brace being given issues on this. Maybe something's wrong with my brain. I'm not understanding why we can't print, why the whole thing is acting like this now. Okay, so we can't linearly interpolate we can't. I'm not really certain why I couldn't print that there. We're using string interpolation, but for some reason, not allowed to do. I think I'm just on vacation brain. Yeah. I'm sure the solution is blatantly obvious, but I just can't see it right now. Line 68. We pre-insert 99 is just 100. Post-insertion is 199. Okay, so what if I remove 199? And then what if I try to push a new node back on again? I'm pretty sure it's just the way that we're handling the pointer is just nonsensical. We need to draw it, but I just don't have I don't have the iPad with me right now, so it's a little bit hard to visualize. This dot const temp, right? This dot tail dot previous. The list is empty. It should be head. All right, we'll say temp dot next is equal to the node. Okay, node dot previous is equal to temp. Node dot next is equal to tail. This dot tail dot previous is equal to the node. Are we missing a pointer? When we remove an element, so we have H, 3, and T. Let's just say we have no elements. And let's have another case where we have 2 elements, right? Temp is equal to this dot head dot next, which is 3. Right, so now temp is equal to 3. We say this dot head dot next is equal to temp dot next. So we wrap around H's pointer around 3 into 4. We then return 3. Okay, let's just say that there's just H3 and T. We do const temp right, we say this temp is equal to this dot head dot next, which is 3. 3, and I would say this dot head dot next, this pointer is going to wrap around 3 to tail, right? And then we return 3. Now there's just H and T, which is an impossible case. Let's just say this dot head dot next is equal to T. Then we say this dot head dot next is equal to temp dot next, which is null. So we end up losing tail pointer. Should not be possible because the length of the list starts at 0. This only runs if the length is greater than 0. Now we're going to push, right? Let's say we take these 3 cases, right? Now we're pushing on to the end. So we say temp, const temp equal this dot tail dot previous. So now we're equal to 4. We're equal to 4. Then we're going to say temp dot next is equal to node, which we're entering, which is 5. Temp dot next is equal to 5. Right? Now we're going to say this node's previous pointer is going to be equal to temp. This node's next pointer is going to be equal to tail. Tail's previous pointer is going to be equal to this node. Yeah, something's definitely wrong because after we do inserted and we try to print, right, everything's broken. If we do ll.print here, right, we should be able to see what the values are. But we can't. Our linked list is broken. We simply cannot print the values. Oh, my brain is fried. Let's look at a case where we have something like this. We're going to do 3 insertions, right? 99, 98, and 95. Right? Temp, this dot tail dot previous, right, is equal to head in this case. We do temp dot next is equal to this node, which is now 99. Node previous is equal to head. Node dot next is equal to tail. This dot tail dot previous is equal to this node. New length plus equal 1. Okay, now let's insert 98. Or let's just say H99T looks like this, right? Then we shift 1 off, right? Temp is equal to this dot head dot next, so it's 99. This temp is equal to this dot head dot next, which is 99. And then this dot head dot next is equal to temp dot next. Okay, I think I'm seeing the problem here. I think we need temp dot previous, right? If we have H99T, if I just copy this up here, if we have H99 and T, right, temp is equal to this dot head dot next, which is 99. let's say this dot head dot next, this pointer is going to equal to temp dot next, so it's equal to t. Right, we still need to attach t back to h, right? You can see temp dot previous this dot head dot next. Temp dot previous needs to point to this dot head, I think. Temp is equal to this dot head dot next, which is 99. All right, and then this dot head dot next is equal to temp dot next, right? Oh no, we want temp dot next dot previous to next dot previous to equal to this dot head. I think this might have been what we were looking for. All the printing might have slowed this down a lot. So I think if we take out all the printing, yeah, we're printing like many times. Already a vast improvement at 58 milliseconds. It's about 360 milliseconds, which is approximately the same speed, I guess, is of, I think it's about the same speed as the version that's memoized. And I don't know, I'm not even at this point. I'm pretty sure this is constant time insertion at the removal at the front and insertion at the end. I mean, yeah, insertion at the end and removal at the front. So still pretty slow. I guess it would just never, I think it would just never be faster. Maybe it'll just never be faster than the dynamic programming solution. But I think that was a pretty good exercise in implementing a linked list. So maybe we'll return to this following day, and that's a wrap on day 71.